Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Application. In my last class, I discussed about the concept of the radon transform. That I have shown the distinction between X-ray imaging and the CT scan, a computed tomography. This CT scan is nothing but the 3D representation of the object from number of projections. So I can consider number of projections, and from this I can get 3D representation of the object, a particular object. And I have discussed about how to determine the projection. The projection is determined like this: gs theta I can determine from fxy. Fxy is the object. So this class, the last class I am going to continue for radon transform and also the inverse radon transform. So what is the radon transform? If you see the projection of fxy along a particular line that we have defined, that is gs theta. Now what is s theta? S and theta represents the coordinate of the X-ray. So we have the X-ray here, coordinate of X-ray relative to the object. So I have the object, and I have the X-ray. So S theta coordinate, the coordinate is S theta, that is the coordinate of the X-ray relative to the object. And in this case, the S is defined in the range infinity minus infinity. So this is the value of S, the range, and also theta, the range of theta is from pi to 0. So this is the range for S and theta. Now in this case, what I am considering gs theta. Gs theta is nothing but the line integral. This is the line integral. This I am considering the object function is fxy. The image reconstruction problem can be defined as the process of determining fxy from gs theta. Gs theta is the projection. So in this case, I want to determine fxy from gs theta. In my last class, I have shown, suppose corresponding to this line number 1, my equation of the line is 1. That is the equation of the line number is 1. X cos theta plus y sin theta is equal to 0. And corresponding to this, my projection is z0 theta. So if you see here, z0 theta is this projection at this point. And after this, I am considering gs theta. What is gs theta? The projection of the second line. If I consider the second line, so what is the equation of the second line? Equation of the second line is x cos theta plus y sin theta minus s. That is the equation of the second line. And corresponding to the second line, what is the projection? The projection is gs theta. That is the projection of fxy. The equation of the second line is x cos theta plus y sin theta is equal to s. That is the equation of the second line. So if you see this expression, the z0 theta, what is the meaning of this? Z0 theta is the integration along the line passing through the origin of xy coordinate and whose normal vector is in the theta direction, and that is given by z0 theta. And like this, I am considering gs theta. And in this case, I am considering the Dirac delta function, because I am just determining the line integral that is only along the line, particular line, along the line number 1, along the line number 2. After this, I considered the concept of the ray sum. Ray sum expression, if you see gs theta, we have this expression, and after this I am putting the value of x and y, that is in terms of s and u. This is x and this is y, and I am considering, because x cos theta plus y sin theta minus s, that is equal to 0. So it is del 0 ds du. And also if you remember that one, that dx dy is equal to ds du, because this coordinate transformation, that from xy to su, there is no shrinkage and there is no expansion. So that is why dx dy is equal to ds du, that we have considered. And corresponding to this, I am having the ray sum equation. This is the ray sum equation. So what is the meaning of this equation? This is the equation that sum of the input function fxy along the x-ray direction, the direction of the x-ray is this, whose distance from the origin is s. So this distance is s. If you see, this distance is s, and whose normal vector is in the theta direction. So the normal vector is in the theta direction. That is, sum of the input function fxy along the direction of the X-ray path whose distance from the origin is s and whose normal vector is in the theta direction. That is the definition of the ray sum. So, the radon transform is mapping the spatial domain x y into that s theta domain. This is the mapping. So, last class we explained about this concept, the concept of the ray sum, and this is the sinogram. The sinogram we have explained. The sinogram is nothing but the radon transform is displayed as an image, and I have shown some examples of the radon transform. The examples like this, you can see that one is the full circle in the radon transform, and the second one is the thin stick in the radon transform. So, my input is this input, and that corresponding to this, and this is my radon transform. Now, the inverting a radon transform. So, if I want to reconstruct fxy from gs theta, I have to do inverse radon transform. Now, I can get the reconstructed value of fxy from the projection. The projection is gs theta. So, in this example, I have shown reconstructions from 18, 36 and the 90 projections, 90 number of projections. So, inverse radon transform, that is the back projection I am considering, and based on this back projection I am getting the reconstructed image. That is a reconstructed image. That is nothing but the 3D representation of a particular object. So, to reconstruct a particular image or the object fxy, I can apply two approaches. There are many approaches, but in this case I can consider two approaches. One is the back projection method and another one is the Fourier transform method. So, now I am going to explain the concept of the back projection method, and after this the Fourier transform method. So, in this example I have shown here, that is just I am doing the back projection, and after the back projection the image, the fxy is reconstructed from gs theta. I can give another example how to do the back projection. So, in the next slide I am showing the how to do the back projection. Suppose I have one object image, suppose I have the object like this image. Suppose this is one internal structure here, and suppose the X-ray is coming from this side. These are the X-ray. So, corresponding to this, I can determine the ray sum, and because this object is present here, I will be getting the 1D absorption profile something like this. I will show you. So, I will be getting the profile something like this. This is the 1D absorption profile. This actually amplitude depends on the absorption. So, in this case we have the maximum absorption here. So, corresponding to this absorption I have the profile. So, that is the projection in this direction. I am doing the projection along this direction. Okay. Now, I am considering another projection. I am considering the another projection. The angle will be different now. So, from this side I am doing the projection of the same scene. This is the object, the same scene I am considering, but in this case I am getting the projection in another direction. So, the projection will be something like this. This is the 1D projection, because in the object this position the absorption will be maximum. So, corresponding to this I have the 1D absorption profile. This amplitude depends on the absorption. Now, from these two projections I have the two projection, that is I am determining gs theta. So, first projection is this and second projection is this. To reconstruct this object I have to do back projection. So, how to do the back projection? So, here you can see I have the profile, this profile, I am doing the back projection I am doing. So, in this case what corresponding to this portion, if you see corresponding to this portion, duplicating the same 1D signal across the image perpendicular to the direction of the beam. That means this is repeated, this is repeated. That is duplicating the same 1D signal. The 1D signal is this, duplicating the same 1D signal across the image perpendicular to the direction of the beam. Similarly, corresponding to the second one, just I want to do the back projection. So, my 1D profile is this is the 1D profile. Now, I am doing the back projection. And corresponding to this, the same procedure I am applying, So, I have this profile. Now, if I combine these two, the first one and that back projected image, I will be getting this. I will be getting. So, if you see intensity at this particular point, it will be double as compared to this portion, So, at this portion I have the more information. So, this portion I have the most information. Similarly, if I do another the projection in another direction, then again after this we can do the back projection. Suppose in this angle I am doing the projection and back projection, then in this case also you will see the information, the more information I will be getting at this point as compared to these points. So, that like this I can do the reconstruction, that is nothing but the 3D representation of the object. So, in the second in that case intensity will be twice that of the individual back projected image. This back projected image, the back projected image is called the laminogram. The back projected image is called laminogram. So, we have seen that how to do the back projection. So, first I am doing the projection in one direction, and again I am doing the projection in another direction, and after this I am doing the back projection, and after this I am combining. So, like this I can get the back projected image. That means I am reconstructing the object. The reconstruction is possible. Now, I will discuss the concept of inverse radon transform, and in this case I will discuss the back projection method. So, what is the back projection method? So, already physically I have explained what is the back projection. So, this expression you know, that is the radon transform, the GS theta, that is the projection GS theta corresponding to the object is fxy. Now, let us consider the back projected image for a particular angle. The angle is theta k, that is given by the theta k, particular theta is fixed. Corresponding to the theta k, I am getting f theta k. So, in general I can write like this, this expression I can write like this, f theta xy dx cos theta comma y sin theta comma theta. That means the theta is fixed, corresponding to theta I am getting f theta xy. So, in this case what we have to do, how to get a particular projection. So, I am explaining again the particular the projection I am getting, the theta is fixed and we are varying the variable s. That means we simply sums the pixel of fxy along the line defined by the specified value of these parameters. So, parameters are mainly s and theta. So, that means we have to first fix theta and we have to vary s. So, theta is fixed and vary s. So, vary s. That means we are summing the pixels of fxy along the line defined by the specified values of these two parameters, the parameters s and theta. So, I can increment the values of s, that means this is to cover the image, but in this case I have to make theta fixed. So, if I make theta fixed, then I will be getting one projection. So, I will be getting one projection. Like this I will be getting number of projection. So, in this figure you can see, so corresponding to this particular angle I am getting one projection, corresponding to this angle I am getting one projection, corresponding to this angle I am getting one projection. After this what I am doing, I am just doing the back projection in this direction, the back projection I am doing like this, I am doing the back projection. So if you see the intensity value at these points, all these points, if you see the information at these points, so I will be getting maximum information because of the information from this, information from this, and information from this. That means I can get 3D information, that is 3D representation of the object. So ultimately the back projected image fxy I can determine by using this expression, because the theta varies from 0 to pi. So for all the angles I am considering, and I am determining fxy, and I have shown this one. And if I consider a discrete value, then instead of integration I have to consider summation. So discrete values, if I consider the theta 1, theta 2, theta 3 like this, so then in this case instead of considering the integral, I am considering the summation. If I consider only the discrete directions, then approximate reconstruction, this is approximate reconstruction is given by this expression. So it is 0 to pi gx cos theta plus y sin theta comma theta d theta. So in polar form also we can write this expression, that is the approximate reconstructed value of fxy. So this concept is quite important, that is the concept of the back projection. So how to get a particular projection? Already I have explained. The projection you can get corresponding to a particular theta. The theta is fixed and we vary s. After varying s, so that it will cover the entire image fxy, then corresponding to this I am getting one projection. After this I am changing theta, and the same procedure is repeated, and corresponding to this I am getting another projection. So like this I will be getting number of projections. After this I will go for the back projection, the back projection of the profile, the gs theta, and from this I am getting fxy. So this is the concept of the back projection method, by which we can do inverse radon transform. The next method is the Fourier transform method. So inverse radon transform by Fourier transform method. So what is the Fourier transform method here? The one dimensional Fourier transform of radon transform, that is gs theta, and corresponding to gs theta I can determine the Fourier transform, that is the one dimensional Fourier transform I can determine, and that is g theta epsilon. And after this, that is for the variable s denoted by g theta, and one cross section of the 2D Fourier transform of the object. So I can determine the 2D Fourier transform of the object fxy sliced by the plane at an angle theta with fx coordinate, fx is the frequency coordinate, and perpendicular to the plane is fx comma fy, that is denoted by this fx minus fy. So this will be identical. So this will be identical. So I am considering the one slice of the 2D Fourier transform of the object. So pictorially I am going to show this projection theorem, so then you can understand what is the projection theorem. So mainly for the time being you can see, so I am determining gs theta, and after this I am taking the 1D Fourier transform of gs theta, that is 1D Fourier transform of radon transform I am determining. After this, that is defined by g theta 1, and after this I am determining the 2D Fourier transform of the object is fxy, and I am determining the 2D Fourier transform of the object is fx comma fy, that is the Fourier transform of the 2D Fourier transform of the object. After this we are considering one slice of this Fourier transform, one slice I am considering. The slice, that is the slice by the plane at an angle theta, with fx coordinate is the frequency coordinate, and perpendicular to the plane fx fy. So I am considering one slice of this. So then g theta is equal to f that epsilon cos theta, epsilon sin theta. So this is identical. So how to prove this one? So first what I have to do, I have to determine the Fourier transform, that is 1D Fourier transform of the radon transform. So first I have to determine this. So this is my gs theta, that is the radon transform, and this is the expression for the Fourier transform, 1D Fourier transform of radon transform. 1D Fourier transform of radon transform I am determining. After this what I am considering, you have the g theta, this one g theta I have, and in place of gs theta, that I have the equation for the ray sum equation, that already I have defined. The ray sum equation I am just putting here, the ray sum equation. So just putting the ray sum equation in this expression, then I will be getting this one, and also I am considering dx dy is equal to ds du. That already you know this. So this condition I am considering. So this is the ray sum equation already I have defined. So from this we are getting this. Now what is g theta? G theta is fxy e to the power this expression. I have this expression. If you see the previous slide, this s cos theta minus u sin theta, that is nothing but x, and s sin theta plus u cos theta, that is nothing but y, that is y. So corresponding to this I have fxy e to the power minus j twice by epsilon x cos theta plus y sin theta dx dy. So I have this expression, and after this expression I can write in this form. You can see, just you can just put minus j twice by epsilon x cos theta epsilon y sin theta dx dy. I will be getting this one, and finally this can be written like this, just combining this one. So one portion I am combining like this, another one is epsilon sin theta. So this expression is very much similar to this expression. If you see f u v minus infinity infinity fxy e to the power minus j x u plus y v and dx dy. This is u v, this is v. So this is nothing but the 2D Fourier transform. This is the 2D Fourier transform of fxy. This is the expression for 2D Fourier transform of the fxy. So if I compare this the 2D Fourier transform and this one, you can see by comparison of this you will be getting fuv. What is fuv? F, what is u here? U is epsilon cos theta. What is v? Epsilon sin theta. So you are getting this one, g theta epsilon is equal to this one. So that means the projection theorem is proved. So pictorially I want to explain this one. So what is the meaning of this projection theorem? So this is the projection theorem, that is one dimensional Fourier transform of the Redon transform. So what is this? So if you see here, I am showing the projection here. The projection is gs theta. So projection along this direction, this is the projection I am considering. I can determine 1D Fourier transform of gs theta. So 1D Fourier transform of g theta is g theta I am getting, corresponding to the frequency variable epsilon, corresponding to this. So first I am calculating the 1D Fourier transform of the Redon transform. Now suppose corresponding to this object, the object is fxy, I am determining the 2D Fourier transform of the object. So the 2D Fourier transform of the object is fx fy. So this is the 2D Fourier transform of the object. Now I am considering the one cross section of this. The cross section is, I am considering this red line, I am considering this is the cross section I am considering. The cross section of the 2D Fourier transform of the object I am considering f epsilon cos theta epsilon sin theta. So one cross section I am considering. This cross section is mainly the cross section of the 2D Fourier transform of the object sliced by a plane. The plane I am considering, you can see, by a plane at an angle theta, with respect to the coordinate fx, and this plane is perpendicular to the plane is fx comma fy. So I am getting one slice. So slice means the cross section of the 2D Fourier transform of the object sliced by a plane at an angle of theta with respect to fx axis and perpendicular to the plane is fx comma fy. So that is the plane I am considering. So this is the one cross section of this. This cross section and the 1D Fourier transform of the Redon transform, that is identical. So if you see the expression, that is the 1D Fourier transform of the Redon transform, I am getting this profile, and if I consider the one slice of the 2D Fourier transform of the object and I am taking one slice, then it will be identical. So projection at an angle theta generates one cross section of fx fy. So the projection of theta at a particular angle theta, it will generate the one cross section of fx fy. So, I am repeating this. So, projection at an angle theta generates one cross section of fx fy, that is the Fourier transform of the original object. So, if I consider the projection for all the thetas, so for all the angles, they will generate the entire profile. The profile is this profile fx fy, and after this, if I take the inverse Fourier transform of this, the inverse Fourier transform of this, that will give fxy. So, if I take the inverse Fourier transform, that will give fxy, that is the reconstructed fxy. So, this projection theorem I have explained, I am again explaining this. So, projection at a particular angle theta generates one cross section of the Fourier transform. So, one cross section of the Fourier transform of the original object. The original object is the Fourier transform of the original object is this, and the projection for all the theta, it will generates the entire profile of this, and finally, I can determine the inverse Fourier transform of this Fourier transform to get the reconstructed fxy. So, this procedure I can consider the how to actually reconstruct fxy. So, the steps I can consider, the first step may be take projections. So, at different angles I can take the projections, that means in this case I am considering gs theta. After this, what I have to do? I have to determine the Fourier transform of the Redon transform, Fourier transform of gs theta, that is the 1D Fourier transform. So, this Fourier transform is nothing but the 1D Fourier transform, 1D Fourier transform of gs theta, that I can. So, 1D Fourier transform I am getting this profile. So, like this I have to consider all the 1D Fourier transform and I have to combine. After combining, I will be getting fx fy, I will be getting, that is number 3 step. Number 3 step is this, and number 4 I have to do inverse Fourier transform of this, inverse Fourier transform, that will give the approximate value of fxy, that will give the approximate value of this. So, these steps, this is the steps of the projection theorem, that is the by using the Fourier transform method we can determine the reconstructed fxy. And one thing is important. So, in Redon domain, suppose Redon domain, that means if I take the 1D Fourier transform, that means I will be getting 2D Fourier transform. So, I will be getting 2D Fourier transform. From 1D Fourier transform I can get the 2D Fourier transform, because you can see this is the 1D Fourier transform. So, if I combine all the 1D Fourier transform, then I can get the 2D Fourier transform, that is 2D Fourier transform is this. And also I can determine 1D wavelet transform. That wavelet transform I am going to discuss in my next classes. So, 1D wavelet transform, and that means in this case this transformation is called a very important transformation, the Regilet transformation. So, how to get the Regilet transform? First I have to determine the Redon transform, and after this I have to consider 1D wavelet transform, then in this case I will be getting the Regilet transform. So, one is the 2D Fourier transform, another one is the Regilet transform I will be getting. So, here I have shown some reconstructions by considering the back projection method, reconstruction from 32 angles, and another example I am considering reconstruction from 64 angles. So, up till now I discussed the concept of the Redon transform and also the inverse Redon transform. So, Redon transform is nothing but the gs theta. From GS theta I can reconstruct fxy. That two methods I have explained, the two approaches, one is the back projection method and another one is the Fourier transform method. In the back projection method I have already explained. So, how to get a particular projection? You make theta fix and vary s, the variable s, and corresponding to this I will be getting one projection. The projection is GS theta. Like this I will be getting number of projections. At a particular time the theta is fixed and varying s, and I will be getting one projection. Like this I will be getting number of projections. So, from all the projections the GS theta I am doing the back projection, and by using the back projection I can reconstruct the image. The image is fxy. This is one popular technique, that is image reconstruction by the back projection technique. The second technique is the Fourier transform technique. In the Fourier transform techniques, what we have to consider, 1D Fourier transform of the Radon transform I have to determine, and also you can see the 2D Fourier transform of the object I can determine, that is fxy is available. So, from this I can determine the 2D Fourier transform. So, in this method, in the Fourier transform method, what I have to do, I have to determine all the 1D Fourier transform of the Radon transforms. So, I have the GS theta because I have the number of projections. For all these projections I can determine the 1D Fourier transform of the Radon transform I can determine. After this I can combine all these 1D Fourier transform, then I will be getting the 2D Fourier transform of the object. After this I have to apply the inverse Fourier transform technique to reconstruct the original fxy. So, this technique is called the Fourier transform technique. So, these two techniques, the two approaches are very important, the back projection approach, another one is the Fourier transform approach. So, I think we have covered the concept. The concept is the 3D representation of a particular object from number of projections. So, let me stop here today. Thank you.